Hi, my name is Gustavo, and today I'm going to present a fast heuristics for the travel salesman problem with multiple flight sidekicks. This research was conducted by me and my advisor, Dr. Marcus Hitch. This is our agenda for today. First, an introduction, where I present the motivation behind the problem. In section 2, I'm going to better characterize the problem that the heuristic addresses and define the challenges we have to solve in order to get a solution. In section 3, we are going to see how the heuristic works. Section 4 presents some computational experiments that assess the performance of the heuristic and compare it to the state of the art. Lastly, in section 5, we show some conclusions. In the last few years, drones have become increasingly mature, widely available, and cheap. All these factors are leading to a growing interest in using drones for supporting the delivery of goods to end customers. Several companies like Amazon, FedEx, and the Brazilian food delivery platform iFood have made public their plans to adopt drone-assisted delivery to their supply chain. This decision, however, implies several operational challenges, like the optimal planning for the delivery operations, which is the focus of our work. More specifically, our work is concerned in how to coordinate the actions of a delivery truck and a set of drones in order to minimize the overall delivery process. Before presenting the proposed heuristic algorithm, let's define more concretely the problems we are interested in and see some of the sub-problems we have to solve in order to get a solution. Suppose we are at a depot with a truck full of packages and a set of drones. Each package has an owner, let's call it a client, and it's our obligation to deliver each package to its owner. It's our choice to decide if a package will be delivered by truck or by drone, as long as it's delivered. For simplicity's sake, we also assume that the drone launches and receives can only be drawn at client locations, but not in between. Our goal, then, is to depart from the depot, deliver all packages, and return to the depot in the minimum amount of time. For example, consider an instance of 8 clients. Suppose we have 2 drones at our disposal. Our first task is to decide which clients will be serviced by truck and which by drone. Then we need to define the route that the truck will follow. It's important that the route starts at the depot, visits all truck clients, and returns back to the depot. With the truck route in hand, we need to assign a drone for each client that is not visited by the truck. Furthermore, we also need to assign a launch point and a receiving point for each time a drone is going to deliver a package to a customer. We call the process of a drone delivering a package to a customer a sortie, and denote it as V, E, I, J, K, where V identifies the drone, I identifies the launch point, G identifies the client that will be serviced, and K identifies the receive point. We also have to respect some additional constraints in order to have a complete solution. First, it's necessary that the truck is always present for a launch or receive activity. It's also not allowed that any kind of activity is done in parallel. For example, suppose that the truck is at a node I and it must serve the client I, receive a drone, and launch a drone. It's our obligation to define a sequence of events, like deliver package to client, receive a drone, and launch a drone, or maybe receive a drone, launch a drone, and deliver package to client. The next constraint we need to respect is the limited endurance and capacity of a drone. That means that there may be clients that are too far or have packages with too much weight. In these cases, we need to ensure that these clients will never be assigned to a drone. Finally, it's necessary to define a precise schedule of our activities, that is, the time that each activity will occur. A mathematical formulation of the problem, that here was defined in an informal way, was proposed by Murray and Raj. We followed the formulation in this work. They also proposed a math heuristic to solve the problem, and in section 4 we will compare the results with ours. Well, in summary, in order to get a complete solution, we need to find a partition of the set of clients into truck clients and drone clients, define the truck route, define a sortie for each drone customer, and define a schedule of all activities. Here's an overview of the main components of our heuristic. On the top level, it uses a multi-armed bandit strategy to search the space of partitions. For every partition, we obtain a truck route by solving a TSP. With a partition and a truck route in hands, we created sorties by running a matching-based algorithm. This solution is then refined by a local search for better partitions and a local search for better sorties. Each time we need to assess the performance of a solution, a schedule of activities needs to be defined. For this task, we propose a fast grid scheduler that gives good approximations of the optimal schedule. At the end of the search, we compare the solution value with an optimistic lower bound. If the solution value exceeds the lower bound, then we recalculate the schedule using a mathematical model seeded with the grid solution. In the next slides, we are going to see each of these components in detail. The multi-armed bandit selection strategy approach is inspired by the epsilon gradient strategy described by Sutton and Barton in Reinforcement Learning, an Introduction. We start by learning some notation. Let capital C denote a set of clients, and C0 denote the set of clients plus the depot. Note that we use the number 0 to represent the depot, and positive integers to represent clients. We also use capital T to denote the set of clients that are serviced by truck, and capital S to denote the set of clients that are serviced by drone. The multi-armed bandit selection strategy is motivated by the fact that the number of truck customers of an optimal solution lies in a finite interval of values. More specifically, for a given instance, the value lies in an interval that is bounded by the minimum number of clients that must be serviced by the truck and the number of clients of the instance. More information about how to calculate the minimum number of clients that must be serviced by the truck is available in our article. With this fact in mind, we create a solution as k for each possible value of k. In addition, we also keep track of the average objective value of sk for each trial of k. Let's call this value qk. At each iteration, we choose a value of k. With probability epsilon, the value of k is chosen randomly using a uniform distribution. Otherwise, we choose the k with the minimum value of qk. In other words, we select the k whose associated solution sk achieved, on average, the best objective value so far. So, with a value of k selected, two scenarios are possible. If sk is defined, that is, we already have a feasible solution stored in sk, then we apply a local search in sk. If sk is undefined, then we construct a solution with k-truck clients. This construction guarantees that every solution sk will have, at least in the first time that k is selected, a solution with k-truck clients. As we will soon see, as k is selected more than one time, the number of truck clients in sk may not be equal to k due to the local search. Some additional remarks. The value of qk is initialized with 0 for each possible value of k. In this way, it is extremely unlikely that some value of k will never have a trial. If a value of k is chosen and we cannot construct a feasible solution for k-truck clients, then we need to apply a penalty to this value of k and update qk accordingly. The value of the penalty is beta times Cmax of Sn, where beta is a penalty factor and Cmax of Sn is the value of a TSP tour that visits all clients. Finally, the selection stops after gamma times the size of the interval of possible values of k, that is represented by this expression here. The purpose of gamma is to control the average number of trials of each value of k. The best solution found is returned. In the last few slides, we assumed the existence of a method to construct solutions with k-truck clients for a given value of k. We also assumed the existence of a local search. In the next sections, we will explain both of these components. First, let's see how to construct a solution with k-truck clients. As we saw earlier, we need to find the partition of the clients into truck clients and run clients. We define the truck route and the sorties, and define the schedule of all events. Here, we also have the additional restriction that the number of truck clients must be equal to k. The partition of the clients is random. It's important to note that the partition needs to respect the capacity limitations of the drones. In other words, we have to make sure that during the partition process, all clients with packages that are too heavy must be assigned to the truck. After the partition is created, we define the truck route by solving a TSP. In our implementation, we use the Link-Cardigan-Hasgan heuristic to solve the TSP. Lastly, as was previously mentioned, we use a matching-based algorithm to find a good initial allocation of sorties and a grid scheduler to define the schedule of activities. Let's see how the matching-based algorithm works. First, we need to introduce a layer more notation. We call tau ij the time the truck takes to travel from the client I to the client j. For drone travel times, we use a similar notation. Tau vij denotes the time the drone v takes to travel from node I to node j. Launch, receive, and drone service activities have an associated time. We call SVI the time the drone v takes to deliver a package at client I, LVI the time required to launch drone v at client location I, and RVI the time required to receive drone v at client location I. As we know, drone endurance is finite, so we denoted EO, the maximum amount of time that the drone V can stay on air while executing the sortie O. Lastly, we denote the truck tour as pi, where pi I is the client visited by the truck in the tour. Here we present a timeline to illustrate the use of the notation in a scenario where a truck is at a client pi I. At time t0, the truck starts the launching process of the drone V and then immediately departs to client pi I plus 1 at time t1. After arriving at time t4, it receives the drone V. The drone V, after being launched at time t1, travels to client j and arrives at time t2. The delivery activity of the package to the client j takes time svj and ends at time t3. The drone V then travels to client pi I plus 1 to be received. The receive activity of the drone V starts at time t4 and ends at time t5. In this example, we are assuming that the truck and the drone V arrive at the client pi I plus 1 at the same time, but that's usually not the case. With all this notation in mind, we are ready to learn the workings of the matching-based algorithm. The algorithm restricts the set of available sorties to those which have the receive point immediately after the launch point in the truck route. The motivation behind this restriction is that now we do not need to worry about overlapping sorties that use the same drone, as depicted in the figure. With the sorties that respect this restriction, we build a complete bipartite graph. We construct the graph so that all possible sorties are on one side and all drone clients are on the other side. Each sortie that respects the imposed restriction can be represented only by the starting point, the drone used, and the serviced drone client. With that in mind, we need to connect each combination of starting point and drone to each drone client. For example, consider this tie instance with 4 clients and 2 drones. To understand how the graph was built, let's focus just on the depot. Every sortie that starts at the depot must end at client 4. There are 2 available drones, so we create 2 drones in the graph. For each of the 2 combinations of depot and drone, there are 2 possible clients to attend, so we create these 4 edges. The same logic applies to the other nodes and edges. The next step is to assign a weight to each edge. The weights are based on a sortie delay estimate. Suppose a generic sortie O. The estimated delay is the time necessary for the drone to complete its mission minus the time necessary for the truck to travel from the launch point to the receive point. This estimate assumes that the launch of drone V is the last activity done by the truck at the client pi. That is, the truck immediately starts traveling after the drone launches. It also assumes that the receive is the first activity done by the truck at the client pi plus 1. Before assigning the estimate delay to the edge, we need to check if the sortie is not infeasible due to endurance limitations. To execute this check, we need to consider 2 times: the flying time of the drone to complete the mission and a possible waiting time for the arrival of the truck. We estimate the waiting time by subtracting the drone mission time into the truck arrival time. If this value is negative, that is, the truck arrives first at the receive location, then we set this value to 0. The total flying time, then, is the drone mission time plus the waiting time. We also introduce a safety margin of p seconds to reduce the probability of an infeasible solution due to endurance limitations. Finally, if our estimates indicate that the sortie is infeasible, we set the edge weight to as infinite. Otherwise, we set it to the delay estimate we calculated earlier. The next and final step is to solve a linear assignment problem to determine the best matching between sorties and sortie customers. With this construction, we aim to reduce the trucking waiting times in the road. For solving the linear assignment problem, we use the implementation LABGAV of Johnson and Vogelnut. Here's an example of the final result using the tie instance we introduced earlier. If after solving the assignment problem the edges colored in red were selected, then these would be the created sorties. We will now turn our attention to the problem of defining a schedule of events. Recall that a schedule, in this context, is a sequence of all the events that occur at a truck stop, that is, drone launches, client service, drone receives, and truck arrival and departure. It's important to find a good schedule because it determines the amount of idle time that is required when the truck has to wait for an incoming drone at subsequent stops. To solve the schedule problem, Murray and Raj proposed a mixed integer linear program called P3. In their computational experiments, they used a time limit of 5 seconds and an optimality gap of 3%. This approach allows us to find close to optimal schedules in almost all cases, but also increases the runtime a lot, which in turn imposes a strong limitation on the exploration of the optimization landscape. Here we propose a simple lower bound and a faster grid scheduler that often finds good and sometimes optimal schedules. We use the grid scheduler throughout the whole optimization procedure. In the end, we compare the obtained solution with the lower bound and, if they do not match, we run P3 with a time limit of 25 seconds and an optimality gap of 0.1% in order to try to improve the solution by finding a better schedule. The lower bound calculation takes as a parameter the truck turn. It assumes that the trucker never needs to wait for a drone to arrive. With that in mind, we can calculate the value by adding the total cost of the route and all the time that is spent launching or receiving a drone or servicing the truck client. Now, let's see how the greedy algorithm works. At a client stop, we classify all events into 4 priority classes. From high priority to low priority, we have urgent landings, starts, normal landings, and serving the truck customer. We consider a landing urgent if the drone, after arriving, cannot wait to be recovered due to endurance limitations. When creating the schedule, the priority class of an event is used to define an ordering. Also, events classified as start are further ordered by non-decreasing total travel time. Each event is associated with a time window. The time window of an event defines its earliest possible occurrence and the latest possible occurrence. Time windows are important especially for landing events. Other events that have no restriction are handled as having a time window of 0 and infinity. The processing order then first considers events whose earliest times before are at the current time. If there are more than one possible event, we use the priority class to choose between events. When an event is chosen and processed, time advances correspondingly. There are 2 important cases we need to consider. First, if there is no available event, the truck needs to wait until the next event becomes available. Second, if there is a not processed event whose latest possible occurrence time is before the current time, then we stop and report an infeasible solution. With the grid scheduler, we now have all components needed to build a complete solution. It still needs to be explained, however, the local search. The local search tries to improve a solution by moving clients from the truck set to the drone set, and vice versa. The number of moves tried during a call to the local search is fixed and is determined by a parameter phi. There are 5 types of moves made by the local search. It's possible to turn one truck client into one drone client and vice versa, turn 2 truck clients into 2 drone clients and vice versa, swap a drone client and a truck client. The type of move and the clients involved are chosen randomly at each iteration. After a move is chosen and applied, we build a turn and allocate the sorties using the procedures described earlier. Before calling the grid scheduler, we apply 2 tests to try to predict the feasibility of the solution. First, we calculate the lower bound for the solution. If the lower bound value is greater than the value of the best solution found so far, then we discard the current solution and go to the next iteration. Otherwise, we run a simple feasibility check. The feasibility check ensures that no sorties whose associated UAV is not capable of finishing the mission due to endurance limitations, even if the truck departs from I as soon as V is launched and V is retrieved as soon as the truck arrives at stop K. For the solutions that could pass in both the tests, we call the grid scheduler. Lastly, we apply sorties local search. If you recall the description of the matching-based algorithm, a restriction on the former of the sorties was imposed. More specifically, only sorties whose endpoint is immediately after the start point are allowed. The sorties local search tries to improve a solution by relaxing this restriction. At each iteration of the sorties local search, we iterate over all the truck tour stops, except at the pot. If a stop I has an associated idle time, then we select the sortie that is last received at I and shift its landing point forward. It's important to know that before applying the shift, we need to check if the drone, that's called to V, has enough endurance to complete the new mission. We also need to check if V is not used for a launch at client I. If endurance is not an issue, but V is launched from I, then we need to check if there is an unused drone, let's call it V prime, at I. If that is the case, we swap V and V prime in all sorties that depart from I or subsequent tour stops. Otherwise, the C shift is not applied. After a complete iteration through the tour stops, we call the grid scheduler. If a better solution could be found, we go for another iteration. Otherwise, the best solution is returned. Well, this concludes the heuristic description. We will now talk about some computational results that assess the performance of this heuristic. We use a set of instances from the literature proposed by Murray and Raj. This set contains 20 instances with 8, 10, 25, 50, and 100 clients. This sums up to 100 different instances. There are also 4 types of drones, with different speed and range. For each combination of instance and drone type, we also consider a scenario with 1 to 4 drones. A complete experiment then consists of 1600 runs. All runs of the heuristic were made deterministic by fixing the random sync to 0. We also fixed a time limit of 7,200 seconds for a solution to be returned. With that said, this table presents the parameter values used in the experiment. The bandit exploration probability, epsilon, was set to 0.1. The bandit learning parameter alpha was set to 0.1. The penalty factor beta was set to 3. The iteration multiplier gamma was set to 2.5. And the number of iterations in the partition local search was set to 100. Here we present an analysis of the main components of the heuristic. Each line of the table is the average of a group of instances with the same number of clients and drones. The third and fourth columns represent the contribution of the mathematical model and the DSP solver, respectively, in the total running time. The sixth column shows the percentage of schedules created by the grid scheduler whose objective value matches with the lower bound. The last column shows the percentage of sorties with length 1 in the best solution. Recall that sorties with length 1 are the ones that are created by the matching algorithm. As we can see, the fourth column shows that the TSP solver dominates the overall running time in large instances. In small instances with 10 or fewer clients, the overhead from reading and preprocessing the instance dominates. From column 6, we can estimate the overall performance of the grid scheduler. The collected data shows that about 30% of all the grid-created schedules are optimal, because their value matches with the optimistic lower bound. Lastly, by analyzing the last column, we can see that 60% of all the sorties on final solutions are of the length 1, which shows that the main assumption made by the matching-based algorithm is mostly valid. We now compare our results with the literature. This table shows a direct comparison of our results with those achieved by Murray and Raj. Both results have been obtained on the same platform. In particular, the results of Murray and Raj are based on an execution of their implementation on our platform. In addition to the average running time and solution value, for our results we also present the time to find the best solution. Comparing both approaches, we can see that they take about the same time to produce the final solution. Our heuristic has a slightly higher overhead for small instances, but scales better and produces better results for faster in larger instances. We can also see that our approach is better in 17 of the 20 instance groups. To help with the comparison, this figure shows a plot of all the 1600 instances. On the x-axis we have the best value of Murray and Raj in seconds, and on the y-axis we have the best value of the proposed heuristic, also in seconds. As we can see, With the exception of some outliers that are probably due to not using a mathematical model to create schedules, our approach produces almost always better results, in particular for larger instances. In summary, we have proposed a new heuristic for solving the traveling salesman problem with multiple flying sidekicks. The heuristic combines several components as a multi-armed bandit selection strategy, a matching-based allocation of sorties, and a fast grid scheduler. Our results show that the current methods still have large potential for improvements, both in solution time and solution quality. Future research could try to scale operations to larger instances, maybe with several hundred clients and dozens of drones. Further extensions, such as delivery time windows and routing of several vehicles, could lead to interesting results. Well, that's it for today. I hope you all have enjoyed the presentation, and thank you for the attention.